pyrometer. So radiations produced at high temperature zone can be observed by the pyrometer. Radiations produced at high temperature zone can be observed by the pyrometer. And it can be measured. So here a simple layout of diagram which clearly explains you the working of pyrometer. This is a pyrometer, and here it is filament of, that is a filament of tungsten filament. This is a circuit where current is current reading, and this one is eyepiece. So here tool will be here. Tool, this one is filament. Sorry. Which has T2 temperature, which is nearly equal to the tool tip temperature. Next, T1 is room temperature, or T2 is also called tungsten filament temperature, TF. So here TF equal to filament temperature, which is nearly equal to temperature of tip of the tool. So TF equal to temperature of tip of the tool. So it shows the in eyepiece, if you use that one pyrometer, if it shows empty, then it is, that means temperature of the tip of the tool is equal to the filament temperature. If it is showing filament, then it is either less than or greater than. Heat generated, Q generated, Q is heat, equal to I square RT. We have shown the circuit, electrical circuit here, where we have to measure the temperature, current and resistance of the circuit, and as well as temperature. I square RT, T is the time, sorry. So from that, heat generated equal to heat dissipated. So heat generated equal to heat dissipated. Heat generated is I square RT equal to, based on the radiation formula, sigma A area and T filament power 4. I is equal to the current in the circuit, filament circuit or pyrometer circuit. R is the resistance of the circuit. T is the time. time the current flows in circuit. Sigma B is a Boltzmann's constant. AF is the area of filament. TF, anyway, we have discussed the final temperature of the filament. So substituting that one, you will get the values. If he gives in terms of voltage, you have to substitute in terms of VIT. So substitute and you will get the filament temperature. So pyrometer are measured high temperatures accurately, but low temperatures there is error. Thermocouple is used for low temperatures. Pyrometer measures high temperatures accurately. Low temperatures it gives error. So next one is these thermometer and thermocouple and pyrometer are used only for stationary tools. Pyrometer are used for fixed tools, fixed or stationary tools. So next method is calorimetric setup. This calorimetric setup is used for rotating tools, especially for drilling. So that calorimetric setup is used for before drilling operation. For example, if you take a rotating tool, we are considering here this one as drilling. So consider enclose in an enclosure entire operation such that this is a drilling machine and this is a drill bit. So we are doing drilling operation on the tool. So it has to be enclosed in one closed space. This is workpiece. This is a drill bit. So in drilling operation, keep the drilling operation enclosed as that you can measure the inside temperature. So before drilling operation, heat equivalent is determined. Drilling operation is done for few seconds so that the heat generated in the machining operation is taken by the calorimetric setup. So before building operation, the heat equivalent or temperature inside the heat equivalent is measured. Drilling operation is performed for few seconds. Drilling operation is performed for few seconds. Then again the heat is measured. So the heat generated in the machining operation is taken up by the calorimetric method. Again the heat equivalent is measured. by using calorimetric setup. So increase in the heat equivalent calorimetric setup is determined. So increase in heat equivalent of calorimetric setup is determined. So the increase in the heat equivalent is a proportional to the temperature, average temperature developed, equivalent to the difference in temperature is equivalent to the maximum temperature. So here what they do is, instead of that heat equivalent is nothing but here temperature they will take. So they will calculate T average equal to T temperature before calorimetric setup plus temperature after divided by 2. So T max, tip of the maximum temperature, or T2 as for our old designation notation, T max equal to T average by some number. For the particular tool, the number 0.4 to 0.5. Based on the past experiments, we have to take the value. So these type of questions they won't ask in exam, but here only one point you need to remember is calorimetric setup is used to calculate the temperature of the tip of the tool of rotation. Next one is tool failure. So the tool failure, whenever the tool failure takes place, the surface finish, there are different methods to understand the failure of the tool. Tool failure. So whenever the tool is not performing the machining satisfactorily, the tool is said to be failure. Tool is assumed failure whenever the tool is not performing machining operation mechanical operation, any operation, whether it is drilling, turning, satisfactory. Then the tool said to be failure. You need to replace the tool. So following are the conditions when we use it, we can decide that tool failure. Parameters considered to determine tool failure. First one is surface finish. The surface finish is coming rough, roughness of surface finish is increasing, the tool is said to be failure. If surface finish is becoming rough, then tool is said to be failure. Next one is forces and power. Power required for machining. So if the tool failure takes place, the forces developed will be higher. When tool failure takes place, that forces generated, the forces developed will be higher, and the power required to do the machining operation, power consumed in machining operation, increases drastically. So then we can assume that tool is undergone failure. Third method is temperature at the tip of the tool. So temperature at the tip of the tool. So as temperature is suddenly increases, then the tool is said to be failure. Tool is said to be failure if temperature increases suddenly. Fourth one, color of the chip. So as the temperature increases, the chip color also changes. So normal machining operation, the chip is light blue color. So light blue color is normal machining operation. It is said to be machining is happening satisfactorily. Black color, or it is also called burnt color. High temperature of chip because of bright shiny surface at the bottom of the tool. The chip indicates the machining is taking place with formation of built-up edge. White color gases produced to be high carbon workpieces, indicating the failure of the tool. Another method. So modes of failure. What are the different modes of tool failure are present? First one, failure through plastic deformation. So failure through plastic deformation is one method. Whenever the temperature of the tip of the tool is greater than the hot hardness temperature of the tool, whenever the temperature of tip of the tool is greater than hot hardness temperature, then the tool starts deformation, permanent deformation. So which is called bending. So due to this no machining takes place. So this is because of improper selection of the process parameters and incorrect selection of tool material. This can be taken as abnormal failure by one of the method, abnormal failure only. Next one is failure through mechanical breakage. So mechanical breakage, when it happens, machining is taking place satisfactory. After some time, suddenly the tip of the tool has chipped off. No further machining can be done. During machining operation, when the forces of the tip of the tool increases suddenly, the tool tip is taking mechanically, but sudden rise in forces because of presence of blowholes. Tool failure takes place. So when these forces will increase suddenly, so due to presence of blowholes or hard inclusions, in workpiece. For example, so I am machining one casting component, so cast iron component. There is blowhole here. If there is blowhole, machining till from here to here, suddenly the force, whenever blowhole comes, suddenly the force will increase. Force will decrease suddenly because there is no material to machine. The force will decrease suddenly due to blowhole. So if you look at the diagram, force required, the force at the blowhole point, it suddenly gone down, and again when the blowhole completes, again suddenly increases. So because of this variation in the force, so the tool failure takes place. Even not only blowhole, if there is different material, like if you are machining cast iron component, if there is aluminum small piece of the material, because aluminum is very smooth, so force decreases suddenly and again increases when the material of cast iron comes. So because of the change in the material, also the failure takes place. This is called plastic failure through mechanical breakage. This is nothing with not with temperature or something, but it is due to the breakage. Sound large noise will come. Okay. Next one is failure through gradual wear. So next method is because of wear and tear, the failure takes place. So during machining, the tool is suddenly wears out. During machining, the tool slowly wears out. Any tool wears out after some time and becomes blunt, right? Because then you can't use it for machining. Blunt after some time. Machining operation is not performed satisfactorily. This is called gradual wear of failure. There are three different methods. Methods in gradual failure. First one is crater wear. So crater wear is due to the friction between the rake surface and the chip of the tool. Crater wear is due to friction between the wear taking place. Tool wear taking place on rake face of the tool is called crater wear. So wear taking place on the crater wear is called on the rake face. It is due to friction between chip and rake face of the tool. Friction between chip and rake face of tool. So because of friction between the two surfaces, the temperature increases. The temperature increases, abrasive action of microchips, powder particles present at the chip tool interface. They are acting as abrasive particles. Abrasive action of fragments of built-up bits present on the chip tool interface. Diffusion. Next one is next one is flank wear. Flank wear is due to the tool wear taking place at flank face of the tool, side flank or end flank. Tool wear taking place on flank face of the tool is called flank wear. Excuse me. Tool wear taking place on the flank face of the tool is called flank wear. It is due to friction between it is due to the friction between tool flank surface, tool flank and workpiece. So because of friction between the tool flank and work surface, abrasive action takes place. Diffusion wear. So during machining of ferrous workpieces using diamond cutting tool, carbon atoms started diffusing from diamond cutting tool to workpiece because of ability of absorbing carbon particles by the ferrous material. The diffusion of one metal atoms into another metal during machining of ferrous workpieces using diamond cutting tool. The carbon atoms started diffusing from diamond cutting tool into workpiece. So because the carbon atoms are moving from diamond cutting tool to the workpiece, and on workpiece it will form some extra surface, and on tool it loses the material because the atoms are moving from the tool to the workpiece. So after some point of time, lot of atoms will move from the tool to the workpiece. So that means the material, there is a loss of the material in the wear of the material of the tool. It happens when with the materials who have chemical reaction form new compound. So this is called diffusion of wear, which is a case of diffusion of carbon atoms from tool to the workpiece.